ओके सो काफी कम लोग दिख रहे हैं क्या? तो क्विज रेडी है, ऑल द टाइम वी कैन टेक क्विज, नो प्रॉब्लम. तो एनीवे, सो व्हाट वी आर डूइंग? ओके, algorithms, right? Yeah, I think I skipped to bubble sort, insertion sort, right? Know all that probably, and all those things, you will think anyway. So we were looking at growth of the functions, right? That f of x equal to big O of g of x if mod of f of x is less than equal to constant times mod of g of x, right? It says that fx is kind of upper bounded by that, g of x. So actually, as you know that in the case of uh, calculus or something, people have studied uh, mod of f of x. But normally in computer science, we give definition. We assume that the functions are positive. We say that f of n is big O of g of n if f of n is less than or equal to constant times g of n. But more precise definition is the absolute value definition anyway. I think we have done some calculations for some of the functions. So I think one person is there who is working on my T problems, or three people are working on T problems, which I gave last time. So they are interacting with me. Good. I think last time I gave you which algorithm is fastest for addition and which algorithm is fastest for multiplication. I think some of you might have looked at the internet at least, or try to find out the answer. So these are interesting problems, by the way. So today I am going to do a couple of more examples, and in fact I will talk about. So we talked about big O notation. Now I am going to talk about big omega notation and big theta notation. Okay, this also you know already in data structure algorithms or your competitive programming class. No? Okay, fine. So if you are looking at order of, sorry, if you are looking at that art of computer programming, everything is there, right? So essentially, so I think you might be knowing that there are 15 different types of sorting algorithms, and I think in the notes you will find two of them which I mentioned, but there are many more, for sorting and so on. So after this notation of theta and omega, we are going to, and we'll give some examples as well. After that, we are going to look at another important topic known as counting. Counting is a very essential thing you do all the time, but counting in different scenarios. For simple problems, how do you count? Or for complex problems, how do we count? So we'll do something about counting. Then very famous principle known as pigeonhole principle. Have you heard of that? It's very simple, You have 10 pigeons, and say suppose 9 boxes. So one box will have at least 2 pigeons, right? This is the basic principle, which is quite useful in counting. Also, in computer science, especially showing that the language A and Bn, those kind of things, basically that cannot be accepted. So A and B and Cn cannot be accepted. So it is used in one very popular lemma known as pumping lemma, and pumping lemma is useful in applications in practical computer science. And I think, yeah, so some of the counting stuff we will do. So let me start. So big O of notation, I am again writing that f of x is less than or equal to k times mod of gx. K is known as Borel constant whenever x is greater than k. Sorry, c. So there exist constant c and k such that this happens. This is a big O notation. Okay. Now I'm going to give you another notation known as big omega notation. So again, f and g are functions from integers or reals to reals. We say that f of x is big omega of g of x if there exist constants c and k such that absolute value of f of x is at least c times absolute value of g of x whenever x is greater than k. So you can clearly see that in the above definition, mod of f of x is less than or equal to constant times mod of g of x. Here it is lower bounded by constant times, right? Okay, that is the definition of big. So I think last time I might have done this example 1 plus 2 plus 3 up to n is big O of n square, if you remember, right? So the question is it a big O of big omega of n square as well? The answer turns out to be yes. Let us see how. But before that, actually, let me give one simple example. Suppose f of x is equal to 8x cube plus 5x square plus 7. Now, since 8x cube plus 5x square plus 7 is at least 8x cube for every positive reals, right? This quantity will always be greater than 8x cube, right? There is more into it. So we can say that basically that f of x is like this, right? Okay. So another definition that is quite useful is big theta function. This is kind of combining both. So again, f and g are functions from z or reals to reals. Then we say that f of x is theta of g of x if first condition that f of x is big O of g of x, and second condition f of x is if both the conditions are satisfied, big O of g of x and f of x is big omega of g of x, then we say that f of x is theta of g of x. So basically, it's kind of from both sides we have a bound, right? On the lower side, on the upper side. Okay, now the time is to do some calculations. So remember, these three notations are important. Big O notation, when mod of f of x is less than or equal to c times mod of g of x whenever x is greater than k. Big omega notation, when mod of f of x is at least c times mod of g of x whenever x is greater than k. And third, fx is big theta of g of x if actually in both sides. So there exists constant c1, c2 actually such that, fx is one-sided lower bounded c1 times something and, c2 times something on upper bounded, right? That is, so I would say that I can write it like this, these two combinations. So we say that f of x is big theta of x, sorry, big theta of g of x. So if there exists constant c1 and c2 such that c1 times mod of gx less than or equal to mod of f of x less than or equal to c2 times mod of g of x whenever x is greater than k. So when both the things are satisfied, we say that f of x is theta of. So that means f of x is big O of g of x and f of x is big omega of g of x. Both conditions are satisfied. Okay, so now 1 plus 2 plus 3 n. Look at an example. So we know that this is big O of n square. Why? Because it is n into n plus 1 by 2 and then you can compute, right? So it's easy to show. Now look at 1 plus 2 plus 3 up to n times. is at least, if I ignore first half of it, so n could be even or odd. So I am taking n by 2 elements. So of course I'll put ceiling or floor, whatever it is, right? N by 2 elements, ignoring first half of them, and write down the rest of the stuff. So this will be, if I am ignoring, so basically, obviously, this will be bigger than this quantity. Ignoring first half. For first half, we are left with this from whatever place, right? Now, this I can sum. So ignore first half and sum only the terms from bigger than n by 2. So this is actually nothing but n by 2 plus n by 2, all of them be lower bounded by n by 2 anyway. And how many times? This is actually n minus n by 2 plus 1 times by 2, which is at least n by 2 into n by 2 is equal to n square by 4. So we have found that for n greater than 1, this quantity is lower bounded by n square by 4, right? So C is equal to 1. So that means we have this result that 1 plus 2 plus 3 plus dot 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 n is big O of n square. Now, since this is this and this implies that 1 plus 2 plus 3 up to n is big theta of n square. Right? So all tricks that you need is inequalities, which is a high school stuff, right? Or now high school maybe 10 plus 2, right? Inequalities. And I think if your inequality subject is still weak, I told you to read that book by G.H. Hardy, Inequalities. A must for every person preparing for IIT JEE, right? I'm sure you might have not seen it, right? Anyway, so, okay, so that's fine. So I think I'll leave. There are a couple of examples which I have already written in the notes. You can look at it. I don't want to do so many examples. The only thing for doing any of these problems is inequalities. That's what you need to keep in mind. How to manipulate the inequalities to find a lower bound or upper bound, right? In all these problems, right? Okay. So remember, we need to find two constants, k and c. So whenever x is greater than k, that condition should be there. And then mod of f of x is either less than or equal to c times mod of g of x, or in the first definition. In the second definition, mod of f of x is at least lower bounded by c times mod of g of x, right? So that's something fairly straightforward. Now I am going to look at the complexity. What is complexity? So there are two kinds of complexities that people study for any algorithm. One is time complexity, and other one is space complexity. And we want to find algorithms which are best in terms of complexity. They take less amount of time, right? So basically, when you are trying to look at some algorithm, you try to compute the number of steps it takes. So I'll give you one example. Only one example is enough, right? And because it's a full subject, it will require one semester to go into look at each and every algorithm. But at this level, at least you should know one of them, one or two, right? This will be useful for your exam also, right? I mean, you have only one exam in your BTech, right? And that is your placement exam, right? Rest of things. So for that, you require these things. Anyway, so I think let me first of all let me show you. Yeah, forget about this. Yeah, this algorithm, if you remember, find maximum element in a finite sequence. I'm going to look at the complexity of this algorithm. So what it does, So input is n integers, a1, a2, an. I'm just recalling it. We have done it last time. Input is a1, a2, an, which are integers. And starting with initialization, max is equal to a1, max is a variable. For I is equal to 2 to n, max is less than ai. So we are updating, right? Okay. So, and then max is basically, if this happens, max we are updating with ai because ai is bigger, right? So so what we are doing in basic in this algorithm is comparing the numbers, right? How many times you are comparing? N minus 1, right? And so from 2 to n, which is n minus 1. So this loop is running, I mean, n minus 1 times, right? N minus 1 comparisons, right? And what else? So let me write it down for you. So this maximum, comparison are the basic operations. So for each I from 1 less than equal to I less than equal to n minus 1, basically 2 to n, right? Loop is running from 2 to n. We are doing two comparisons, right? To determine the end of the list and update the term. Two comparisons to determine the end of the list and updating the term or not, right? And this loop is running n minus 1 time, so total number of comparisons. And actually one comparison we are also doing to exit the loop. Exit the loop. The total number of comparisons are 2 times n minus 1 because loop is running n minus 1 times plus 1, right? Constantly. Now the whole thing is big O of n. This is big O of n. So this is how we do. We just count operations. So this is a very simple algorithm. In more complicated algorithms, there are more operations like addition, subtraction, multiplication, division. So basically, given an algorithm, we decompose into basic operations, right? And we know the complexity of the basic operations, and then we combine them depending upon what kind of loop is running and so on. We calculate the complexity of the algorithm in general, right? Okay, and that algorithm is computed in terms of big O notation. Whatever terms comes, you find out what is in terms of big O, right? The value of in terms of big O. So now, for example, if we look at searching one object out of n objects, what is the worst case complexity? N, big O of n. I have to look at each and every thing exactly once, right, to arrive at the conclusion. But as I mentioned to you, for quantum computers, this is big O of square root of n, which is much better. So obviously, quantum computers are better, right? These computers can only locate an object in n steps that can locate in square root of n. I think, as you know, that Grover's search algorithm, which was discovered for quantum computers, I mean, it has natural connections with your biology as well, right? Apur Patel has shown that there are, why there are 4 nucleotide bases in 20 amino acids in each of genetic material. It is because of quantum computers, the quantum algorithms, especially Grover's search algorithm. So all these interesting connections are there, which sometime you can explore anyway. So this is all about complexity. So linear search. So I am leaving as an exercise for you linear search. Linear search is big O of n. So basically, the worst case complexity will be big O of n. Okay. Time. Okay. So this you can find out that linear search algorithm has complexity big O of n. Actually, it will come to around 2n plus 2 or something, which is big O of n. So you do those calculations. This is the most important thing for you to learn as a computer scientist. Look at a problem, analyze it. Even if you're working in a company, your boss may say that, okay, do this, implement this, right? That person may be only MBA. See, and then he will give you this problem. So you should know how to fool him. You can say that, "Sir, this is exponential time problem we cannot solve. The complexities we go of whatever exponential thing, right? Or so basically, so you should know. And there are, in fact, related problems are like uh, NP complete problems and so on. So, I think you might have heard about NP complete problems or not. These are very interesting things. I think Turing machine, right? So if you can solve a problem with complexity in polynomial time on a deterministic Turing machine, they are known as class P problems. If you can solve a problem in polynomial time in complexity on a non-deterministic Turing machine, it is known as class NP problem. Okay. Got the thing? Understanding? So Turing machine is deterministic and the complexity is polynomial time. Turing machine is not deterministic and complexity is polynomial time. These kind of things are known as class P problems, and these are class NP problems, right? So one can classify P problems, NP problems, and there is a $1 million question that whether P is equal to NP or not. We know that class P problems is subset of class NP problems, right? But whether they are equal or not, that's still an open problem. And I think if you play Minesweeper game, so Minesweeper play game can help you to get $1 million just playing Minesweeper game. If you can solve P versus NP problem, right? So that you can see, right? Anyway, so that's about. Now I'm going to do counting and using this very common sense, in a very common, it's a very day-to-day thing. Suppose if I ask you how many binary strings are there of length n? What will you say? So you know counting already, right? So two choices here, two choices here, two choices here, right? 0 or 1, 0 or 1. So total will be 2 into 2 into 2 and times the 2 raised power n. These things are given in the book as a chapter, right? It's common sense, right? So, okay. So let me ask you some little bit more non-trivial question. How many functions? There are m elements. There are n elements. How many functions f are there from a set with m elements to set with n elements? हाँ भाई. Any idea how many functions from a set of m elements to set of n elements? So first of all, function की definition clear होनी चाहिए, right? For each element in, I can call it set A. How much? पावर में तो होगा, क्या होगा पावर में? n की पावर m. क्यों? So for each m elements of the domain, so a function, so you need to remember, a function corresponds to a choice of one of the n elements, choice of one of elements for each m element, right? So by product rules, how many such elements are there? N into n into n, m times, which is n raised to power m. Right? Something. I can modify this question little bit, and I ask this question: how many one-to-one functions? M elements, n elements. Case 1, m is greater than n. Case 2, m is less than or equal to n. If m is greater than n, how many one-to-one functions are there? कोई भी नहीं होगा. Very good, very good. ये सब तो तुमको आता ही है, right? And what about the second case? Yeah, I mean, you have to not factorial. I mean, I can write it down the value. To 0. And here it is n into n minus 1 into n minus 2 dot 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 n minus m plus 1. These many functions will be there. By the way, these kind of questions are asked in your interview, job interview. So you need to be careful. So remember, I asked you how many reflexive relations, how many transitive relations on a set with n elements, how many reflexive relations. These are the counting business, which are very, very important actually, so, you need to know how to count. Anyway, let me look at some bit complicated problem, how to count as an example. These are the easy things, complex counting problem. Suppose each user of a computer has password, from 6 to 8 characters long. 6 to 8 characters. And what are these characters? It is uppercase letter or a digit. These characters are uppercase letter, means 26 letters, or a digit out of those 10, right? 0 to 9. Now, if I put a condition that each password must contain at least one digit, how many possible passwords are there? Now, this is an interesting question, right? 6 to 8 characters long. So obviously there are three lengths: length 6 passwords, length 7 passwords, length 8 passwords. I have to do counting for each of them separately, right? Now, if I look at length 6, so possibilities are either all alphabets 26 plus 10, 36. So 36 choice for each box, and there are 6 boxes. So total will be 36 raised to power 6 passwords. But I have not put a condition yet, right? What is the condition? One of them should be digit, right? So I can just put some notations here. P is the total number of passwords. P6, length 6 password. P7, length 7 password. P8, total length 8 passwords, right? So by some rule, P is P6 plus P7 plus P8, right? So I have to find out this P6, P7, P8. P6 means how many passwords are there of length 6? How many passwords are there of length 7 is P7. How many passwords are there of length 8 is P8. So I have to find this sum of these three quantities, right? Now the first thing is P6. P6 is length 6, total possibilities will be 36 raised to power 6, because 6 boxes, I have to fill 36 each, right? 36 into 36 into 36, 6 times. Why 36? 26 alphabet plus 10 digits, which is 36, right? Minus, I have to subtract what? 26 power 6, because this is number of strings. The last thing is number of strings with no digit, right? Because इनको तो हटाना पड़ेगा ना. That is, so P6 is 36 raised to power 6 minus 26 raised to power 6. P7 will also be same thing. 36 raised to power 7 minus 26 raised to power 7. And then P8 will be 36 raised to power 8 minus 26 raised to the power 8. Sum कर लो उसको. Calculator चाहिए होगा तुमको, right? Yeah, so I don't also remember. This number is there which I can write. P7 is equal to 36 raised to power 6 minus 26 raised to power, 7, and P8 is equal to 36 raised to power 8 minus 26 raised to power 8. This number turns out to be, so P turns out to be 268,448,306,3360. It's quite big number. So now you see why is we say that एक मतलब एक डिजिट होनी चाहिए एटलीस्ट पासवर्ड में, राइट? या कैपिटल लेटर्स होना चाहिए, एक लोअर केस होना चाहिए, एक स्पेशल सिंबल होना चाहिए, तो नंबर ऑफ पासवर्ड्स बढ़ जाएंगे ना. अगर कोई क्रैक करने की कोशिश करेगा तो डिफिकल्टी होगी, ज्यादा बढ़ेगा, राइट? दैट्स अ रीजन व्हाई. बट दीस डेज पीपल हैव रिटन प्रोग्राम्स, सो यू जस्ट एंटर पासवर्ड इज वीक, फिर चेंज करो, स्ट्रांग, वेरी गुड, राइट? That is the job of computer scientists, programmers like you can do these things, right? But you need to understand the theory behind it anyway. That's about complex problem counting. Okay, another important thing, inclusion exclusion principle. By the way, counting is very, very important in computer science. Whenever you encounter any problem, first you need to enumerate or count what are the cases, how many possibilities, and so on. So that's why this is very important topic. And I think, for example, as a T problem, I can give you how many Hadamard matrices are there of order 4. How many Hadamard matrices are there of order 4? How will you count? How many Hadamard matrices are there of order 8? You are getting my point? How many Hadamard matrices are there of order 4? कितनी होंगी? So now when we are saying कितनी होंगी, we are obviously looking at two matrices will be equivalent if you can just multiply with certain things and get the second matrix, right? So you have to exclude those cases, and you have to come out enumerating how many matrices are there of order 4. How many Hadamard matrices are there of order 4, right? Similarly, order 8. Will there be how many Hadamard matrices are there of order 6? Very good, very good. These kind of questions can be asked anytime in quiz or exams. And then some people will construct. For example, with 22 number of elements, 2-3 people are there who said that I have constructed. This is perfectly correct. So you need to know what is going on anyway. So this principle is really very easy. This is equal to this plus this minus this. What is A1 and A2? I'll just let me explain. So this is number of ways to select an element from A1 or A2. Number of ways to select an element from A1 or A2. A1 or A2. Okay. This is number of ways to select element from A1. This is number of ways select element from A2, and this is number of ways to select an element from both A1 and A2. This is a inclusion exclusion principle, something very common again. Counting is all, experience in daily life, right? How do we count? Number of ways to select an element from A1 or A2, or what is important? Number of ways to select from A1, from A2, and from both A1 and A2, intersection, right? So basically, this principle I am going to apply to count certain binary strings of a special kind. Okay, so let me show you the example. I hope you understand the idea behind it. Question is, how many bit strings of length 8 either start with a 1 bit or end with 2 bits, and 2 specific bits 0 and 0. 8 length bit strings I am searching for. First bit is fixed 1, last 2 bits are 0 0. How many such strings are possible? Here we have to apply this principle of counting. How do we count? कोई अगर कर लेता है तो बताओ मेरे को, right? So how many bits? Let me make a picture so it will be more clear to you. So I am looking for strings. Here it is 1, here it is 0 0. How many such strings are possible? हाँ, very good. 160 किसने निकाला? Very good. कैसे आया, कोई बता सकता है? Yes, बताओ. हाँ?
तो बाद में 6 प्लस बाकी वधी उसमें 0 और 1 की पॉसिबिलिटी से उसकी पॉसिबिलिटी आई 2⁻7. बाद में लास्ट 2 प्लेस में 0 फिक्स कर दिया तो 6 प्लेस वधी तो 2⁻6, और बाद में वो फर्स्ट पे 1 और लास्ट 2 पे 0 फिक्स कर दिया तो 5 पॉसिबिलिटी वधी तो 2⁻5. और
Very good. हाँ? 160, right? You got it? अपने आप ही करना चाहिए ना, मेरे को तो कुछ करने की जरूरत नहीं पड़नी चाहिए, राइट? हाँ? So this is daily common. So we need to count how many strings are there when the first bit is 1. So these are 2⁻7 because एक bit एक fix हो गई, बची 6 places, 7 places. So 2⁻7 choices for those, right? And the last 2 bits if you fix, so 6 possibilities, 2⁻6, 2⁻6 plus 2⁻7, and then I have to subtract the duplications which are 2⁻5, because if you fix the first and last, so five of them are possibilities, 2⁻5. So we subtract that and we get 160. Beautiful, right? The number of strings are 128 plus 64 minus 32 is equal to 160. So now I am going to ask you one more question, and let me see if you can answer. How many bit strings of length 4 that do not have two consecutive ones. लेंथ 4 की बाइनरी स्ट्रिंग्स बनानी है where none of the string has two consecutive ones. How many of them will be there? लेंथ 4. हाँ, कितनी? 13. 13 नहीं यार, 13 तो नहीं होगी. हाँ, who is saying 8? How? हाँ, मैं सुनता हूँ तुम्हारे पास आके.
चार बॉक्स है, उसमें उसकी 2 रेस टू 4 हो गया उसका.
Are there so 16 possibilities?
से माइनस अगर वो दोनों एक को हम फिक्स कर एक साथ में, उसको एक बॉक्स गिन ले तो 3 उसके बॉक्स हो गए, तो -2 रेस टू 8 इक्वल्स टू 2 रेस टू 3.
Anyway, so this is one approach. I am going to tell you another very simple approach, which is known as tree diagram. You just start making tree and automatically it will count. Okay, let me show you that. Okay, so what I am going to do, I am making a tree, a root. So I'm going to choose the first bit of the string, right? The first bit. The first bit could be 1 or 0, right? First bit could be 1 or 0, two possibilities. You can choose either 1 or 0. Both cases I am keeping in mind. Then if I go further, second bit, if this bit is 1, the first bit, second bit cannot be 1, it will be 0. And if this bit is 0, so this bit could be, don't know what is happening here, it could be 1 or 0, right? Then you go to third bit, 1, 0. So if 0 is there, 1 is there, then 1 will not come, 0 will come, right? So I can make, I think I'll show you, but something is happening. I am unable to draw here anything which you see. 1, 0, 1, 0. I think I will let me draw it in a nice manner. Oh, sorry. Then first bit, one, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1. You can see that I'm keeping in mind that the consecutive ones are not there, right? So basically, what are these strings? 1, 0, 1, 0, 1 0 0 1. You can see that Z, right? 1 0 1 0. Then 1 0 0 0 0 1 0 1 0 1 0 0 0 0 1 0 0 0 0 1. All 8 possibilities are there. So basically, this kind of tweak you can make to count. This is the T diagram business for counting. Okay. So if I say that next is pigeonhole principle. If k is positive integer and k plus 1 or more objects are placed into k boxes, then at least one box will have 2 or more objects. Right? Pigeonhole principle. If there are k pigeons and k plus 1 boxes, so one box will have more than 2 pigeons. That's a very simple pigeonhole principle. You might have seen, I had in my younger days, we have pigeons in my house, boxes. There they have learned, right, these kind of things. But anyway, so it's a very simple thing. So that means if I take 367 people, 367, two of them will share the same birthday, right? Why? Because that's 365 total number of days, right? If I take 367, two will they share the same birthday, right? This is a simple observation of pigeonhole principle. By the way, pigeonhole principle can be generalized. If n objects are placed into k, if n, so general, if n objects are placed into k objects, then there is at least one box containing at least n by k objects. This is a simple generalization, can be proved easily, so I am leaving all these things. So many things. Yeah, I think that's all. So next class, we are going to look at permutations, combinations. So it's very easy, right? Counting. So we can do more, especially permutation combination. By the way, as an exercise, I can also ask you what are Catalan numbers? What are Catalan numbers and how they are useful in counting? Catalan numbers are very useful at different places. Okay, Catalan numbers. Right. That's all. Thank you very much. See you next class.